So today we've got Brian Siegelwax. So he's basically he's writing in Medium about quantum computing, and he's got quite some interesting um, posts in here. I definitely recommend you guys to check him out. I was just going and reading through his most recent piece, which is about a swap test, and he kind of goes into detail on how to compare how to use sort of how to use a rhyme for that to compare the different bases, which I think it's quite an interesting. I haven't gone through it completely yet, but it's definitely an interesting piece that I recommend reading. And let's see how he did. Actually, to be honest, the challenge this time was quite tricky, and I'm quite amazed with the way that Brian approached it. And so yeah, I'm gonna leave you guys with the video, and then we'll just join in afterwards for some commentary. Enjoy.
My name is Brian Siegelwax, and this is my quantum circuit puzzle from Quantum Intuition. I want to begin by apologizing for the poor audio quality. I don't have professional equipment available. And also, this is not a live walkthrough. I started doing it, but it was very long, very boring. I tried to think out loud, but there were certain points where there was just too much silence as I was really trying to think. So this is a summary of how I solved it and what I was thinking, but without all of the boring silence stretching it out unnecessarily long. The first thing I looked at was the left side, the input states, where there's a 0, 1, and minus, and those are all very easy to visualize on the block sphere. Next to that is the black box that provides the puzzle. And then on the right side, the 75, 50, and 25%, these are the probabilities of measuring 0 in the z basis, and the goal is to rotate those to 100% so that they say off. And the first thing I noticed was the 75 and the 25, because those are 1/3 and 2/3 pi rotations. But if I zoom out a bit here and look at the tools available to me, I have half and quarter rotations, but not thirds. So I already expected this to be a little challenging just based on that. And then I also decided to start with the middle qubit because it's 50%. That should be the easiest one. Spoiler alert, it's the hardest one, but initially it looks like the easiest one. So let me grab a Hadamard. That's the logical first place to start, and that does absolutely nothing. I need some kind of half rotation to get that 50% to be 0, and that half x rotation changing to 25% makes no sense. And I tried every combination of everything, halves and quarters, and I tried everything I could possibly think of, and nothing worked. So after a while of trying to figure out the middle qubit, I put that on the back burner and I started looking at the top and the bottom. I also tried all kinds of combinations of single qubit operations, and then thought, because it's 75 and 25, maybe multi-qubit operations will be helpful. So put the control in one place, move the target around, move the control around, and tried all kinds of different combinations along with single qubit operations as well. Even tried Toffoli gates in different positions, and long story short, nothing at all worked. The numbers were not intuitive at all, and then I decided to cheat. 75, 50, and 25 are z basis, so let me rotate around and use an ancilla down here, and let's take a look at where we are in the x basis. Let me grab an S dagger and take a look in the y basis and see if that gives me any insights. And also, no help there. I tried every combination of single qubit operations and multi-qubit operations. And the one thing I didn't try, you could call it intuition, I call it desperation. The only thing I didn't try was the Fredkin gate. And eventually I settled on a control in the middle with a swap up top and a swap on the bottom. And now we've got 50, 50, and 50. And honestly, I wouldn't normally think of the Fredkin at all, but I've been using it a lot recently. It's not an operation you see very often, but and so that's why it's last. But the Fredkin is there. We've got 50, 50, and 50. The first logical thing to try is the Hadamard, nothing, nothing, and finally a breakthrough. Here is a Hadamard turning the bottom qubit off. So let's look at the top two, 50 and 50. Let's try, we need some kind of half rotation, but they're not even doing anything. Nothing's working. And the intuition here, again, is if single qubit operations aren't working, let's try multi-qubit operations. And I eventually ended up with a control in the middle, a target up top, and now that shows the top qubit in the on state. And normally a NOT gate would turn an on-off and vice versa. I was skeptical that that would work because of this circuit thus far, but I was pleasantly surprised that I now had 2 off and 1 remaining. The middle qubit showing 50%, first logical thing to try is the Hadamard. Next logical thing to try would be any of the half rotations, and long story short, or fast forward, a half X rotation now gives me off, off, and off, and the puzzle is solved. And I will review that, since that was maybe quick or not clear. The intuition, if you will, for the Fredkin gate was absolutely nothing else worked. So let's put that back here. The Hadamard for the bottom qubit was intuitive in the sense that that's the first thing you should try when you see 50%, the easiest thing to try. Then the intuition for the CNOT was none of the single gate operations were working, or single qubit operations were working in any kind of combination. Then the intuition for the NOT gate was on to off, and the intuition for the half X was getting back to 0 from 50%. And the goal of this video was the intuition in solving the puzzle, but more than that, there's an intuition in why does this solve the puzzle. The Fredkin gate was not intuitive at all in selecting it. The CNOT wasn't intuitive at all. The single qubit operations were intuitive, in short, but the multi-qubit operations were not. So what I decided to do was I reverse engineered the black box to find out why this worked, and I'll give you a very quick summary of that. Inside the black box, there's another Fredkin gate. So the Fredkin gate is a controlled swap. If the middle qubit is 0, it does nothing. If there's a 1, the top and bottom qubits will swap states. But the intuition of what is the Fredkin gate doing, the true answer is it is canceling the Fredkin gate that is inside the black box. So if the middle qubit is 0, both Fredkins do nothing. If the middle qubit is 1, the first Fredkin swaps the states, and then the second Fredkin just swaps them back again. What is the intuition for the CNOT? There's also a CNOT in the black box. So if the middle qubit is 0, both CNOTs do nothing. If the middle qubit is a 1, the first CNOT flips the top qubit, and the second CNOT just flips it right back again. So in a nutshell, the top qubit starts at 0, and then inside the black box, when you remove everything that cancels out, the Fredkins and the CNOTs, you have a NOT operation. So the knot changes the 0 to a 1, flips the 0 to a 1, and then this knot, we've taken out the Fredkin and the C knot, the second knot flips it back to 0. So 0, flip to 1, flip back to 0. Then in the middle we have the 1, and inside the black box is a half X rotation. So we have a half X here and a half X here. When you add half X and half X, you get X, which is a knot. So you start with 1, you apply a knot, and it flips to 0, and that's off. Then the bottom qubit starts in the minus state, and inside the black box is a Z rotation. So it flips from minus to plus, and if you start at 0 and you apply a Hadamard gate, you go to the plus state, which means that this Hadamard here is now canceling that Hadamard and going back to 0, and now we have 3 off qubits. So a combination of the intuition of how I solved it. It was very challenging. It took more time than I'd really care to admit. And the intuition of why it solves it. If you look into the black box, it's basically a mirror image of the solution. It's not a perfect mirror image, but it's very, very close. And that's why it's counterintuitive. You're trying to think, what's the Fredkin doing and what's the C knot doing? And all they're doing is cancellation, which is not something I was expecting. Made it fun, made it challenging, and I look forward to the next challenge.
So, I hope you enjoyed Brian's approach to this. To be honest, I was really surprised when I watched the video. I kind of really like the fact that Brian didn't just try to turn the qubits off, but it kind of, he tried to go the extra mile and reverse engineer what's inside the box. Now, this is almost, I'd say, almost impossible in terms of like there could be anything in the box, right? Like turning the qubits off does not necessarily mean you're uncomputing what the box does, or it doesn't necessarily mean that you're reversing what you have in the box. Because in theory, if I would just open Quirk just quickly, right? Just to add some commentary to this, I just think it's worth, because I was really happy to see how the video was approached. But the idea is, you could have an arbitrary number of rotations in here, right? And then you could just have like, say, 2 times a quarter, and then you could just have like an S gate, right? And imagine this is your black box. You can just turn this thing off with a Hadamard gate. So it does not necessarily mean, okay, those gates are equivalent to a Hadamard rotation. Probably what I'm just saying doesn't make sense. It's not that they're equivalent, but they take you to a similar to the same final state, and so that kind of takes it back to 0. So it's not it doesn't have to be like, I think the second part of Brian's video was not wrong, but it was it definitely could be the inside of the box. But it doesn't necessarily have to be. Nevertheless, I want to take a look into this right now with you guys together, because I think it's worth the time. First, maybe I wanted to take a look at how I, in general, approach or would approach such problems. Sort of give you the intuition, 2 different ways that I could see, or that I would kind of imagine myself solving those problems. Maybe that helps, and maybe just maybe you like it. I don't know. So the first way is, basically, I don't if you don't care what's in the box, which you shouldn't care what's in the box, you kind of want to go about it. First, you need to figure out whether those qubits are somehow entangled. Because if they're not entangled, then it's just a matter of trial and error, different rotations, and that's it, right? So one easy way to see whether they're entangled, other than, of course, playing with gates in here, is you can also try to change the input states and see what happens, right? For example, in this case, if I change the first wire, what's interesting is that I see that the bottom wire result changes. that should already tell you that there is some sort of multi-qubit path or gates that kind of somehow connect these to the like this wire to this wire. It doesn't have to be directly; it can be indirectly, but that's one thing. What's more, and if you do this with the other ones, so this is super interesting because you can see that when I change this one, right, then the opposite changes as well. So the one at the top. So that also tells you that there is something in there. In this particular case, the interesting thing, and I think that's kind of the essence of the whole of this particular puzzle, is that if you change the one in the middle, like kind of everything changes, right? So it means this one must be connected to those two. So that's kind of because if you pay attention, that doesn't matter. The more I change this one, the one in the middle doesn't change, right? So intuitively, wait a second. That might not always be wrong, but it gives you a way to start, right? Like, so what I would do first is I would, assume that what I'm going to try, and again, there might be other ways to do that, but what I'm going to try is, as I see that if I change this one, at some point I'm changing the other ones as well. It might be worth giving it a try first with putting sort of a control here. Let me see, because if I change that, let me see if what I'm saying is, because that doesn't seem to change in this particular case. Yeah. In other cases, okay, it actually in other cases works, but I don't really care. I care just about this particular configuration because it's the one that I'm trying to turn off, right? It's the one that I'm trying to turn off. So in this particular case, it doesn't matter, right? So if I start with the control here, the natural thing that I could think of is just play with some gates and see, okay, that does something, but it doesn't turn it off completely. Maybe there's one that works and turns it off completely. So first I want to try if I can get it to turn it off completely or on, because then it's trivial. Oh, here you go. So this worked. Now we've got one on and we can turn it off. Good. And kind of I'd say I try probably the same here, right? Let me and so this is not turning it off completely. This either, and okay, not completely, but it turns it to 50-50, which is not bad because then we can try if the hardware works, and it works. So it works. And again, I'm half improvising this solution. It's not exactly what's in the box. And now I've got this one left, which hopefully, yeah, that works. So this is another solution. So this is just just to show you a way to approach these, right? So you kind of first need to figure out a strategy, because if the qubits are entangled, like really these puzzles can be reduced to finding out, are those qubits entangled and how? Because then if you disentangle them, then it's just a matter of applying the right rotations to get them back to zero. That's not a big issue, right? So that's one way that I would approach it. Another way that you can approach it is to see if this black box actually implements something you might know or have some intuition about. In this particular example, it is the case. So the internals of the box are nothing else than let me show you. It's a QFT, right? Like these, with a small modification at the end, which is the following gate, right? So this is the, let's see, is this gonna work or not? Where's my mouse? Here it is, but it doesn't work completely as expected. I shouldn't play with plugging and unplugging things. I should learn. So I don't know, what was that? Come on. Let's see if that works. So hopefully the sound is not off. Let me just pause this and quickly. Okay, sound seems to be okay. So this is the, and all this just because I wanted to connect them. Okay, whatever, pencil. So this is the stuff that I added. Okay, and so you might think like, so one way that you could have thought about this is, okay, let's see if there's an interesting pattern in here. Now I'm gonna cheat in here a little bit. Oh no, we can do this here actually. Let's put this back to 0. So what happens when we play with actual binary inputs, right? So 000, 001. We can even probably play better with the X gate. So 001. So that's number 1. That's number 2. That's number 3. One thing that you probably realize is that this indicator here keeps switching between 75% and 25%. It's always like that, right? So whereas this one here kind of does smaller steps, right? So you can, if you had access to the full power of Quirk, you could play an animated gate here that does that for you. Quirk has this really cool counting gate in here, which basically counts for you. And so you can see that basically there is this, this pattern in here, and then here's like 50%, 32, 25, 32, 50, 67, 75. And it kind of keeps doing this, right? This is something that if you've got some intuition about the QFT, you could probably recognize. It's a bit stretched, okay? So I wouldn't expect anyone to figure this out. I would certainly not figure it out, I think. But this is basically the way the QFT basis works, right? So let me trash this for a second and let's take a look at what happens with the QFT. So the QFT, pay attention at the block spheres here. It switches from plus to minus, plus to minus, plus to minus. This one does a bit of a, more granular steps. This does more granular steps, and this does more granular steps. Now, this could tell you that, maybe there's a chance that what the black box is a QFT with some slight modification that makes this pattern appear in the amplitudes, because the QFT doesn't show this pattern in the amplitudes if you pay attention, because everything happens in Z base. So there has to be some sort of rotation in there that makes this happen, and so this could be, could kind of lead you to think about, okay, maybe there's something here off because this one doesn't show anything. There could probably be a control in here. And this is how you could maybe figure out that in particular that rotation does this for you, right? So and kind of that would then uncompute these, and then you kind of realize, okay, now I've got a QFT, and so now I know how to deal with it. Yeah. Now this is a really stretched idea. I don't know if I would even be able to think about it this way, especially if I not having the block spheres in here. That would take quite some effort. Maybe I could, maybe I could just kind of go into the Hadamard bases. And see what happens exactly. So now you can see that if I do these right, sorry, it's going to be better if I use these gates, these. So now you kind of see the pattern, right? Yeah, so you start seeing the pattern in here. And then you just uncompute it by uncomputing the QFT. But that's really stretched, as I said. It's just another way. You can try to see, is there anything in the box that makes sense? Maybe there's a pattern that I know about that I could figure out by playing with the inputs. But if you just go and want to speed run the thing, want to turn the qubits off, then you're better off by just basically kind of reasoning about, okay, are the qubits entangled? If they're entangled, how do I disentangle them? And once I got them disentangled, then I can try to rotate stuff. You might have to combine things in between, but that's basically the way that I would approach it. Yeah, and I don't want to take much more time. I think I'm going to do a follow-up video trying to explain why Brian's solution also works, and how that Fredkin gate and that control swap gate actually makes the effect that kind of creates the effect that it does. Because I think there might be some interesting intuition there as well. For you guys to learn from these. Yeah, I hope you enjoyed the video. It was a bit of a longer one this time, but I thought it was fun. I thought I'd drop a couple of comments on how to approach these problems, because I think they're fun and interesting. So stay tuned for more next time.